chapter 3, we talked about the conservation of mass and energy. Conservation of energy is the first law of thermodynamics, and we'll be applying that to a variety of applications for open and closed systems. But first, we want to look at the conservation of mass. So for a closed system, it's trivial. Conservation of mass, we said closed systems were this constant mass, so that's all it is. For an open system, it's a different situation, and here we want to take the constant mass of a closed system and do a coordinate transformation into a constant space system. So what I recommend is that you look at the details on page 49 of the text. And this goes through it in great detail and shows the calculus behind it, but to give you an overview of what happens very quickly, we'll have this. So this is a control volume in space. So think of this is only two-dimensional that you see, but think of it as three-dimensional, and I'm going to have fluid flowing through it. So here I have the fluid flow is flowing through it. And what I'm going to do is here's the boundary, and here's the boundary at time t. So at time t, you turn on a strobe and you capture the fluid that's in there. Then blink at time t plus delta t, the next strobe, some of the fluid is moved out. And now what happens is that mass, that constant mass at time t, has shifted out, and we have regions of space 1, 2, and 3. And so what happens is we take the control mass that we knew that we identified at time t with the strobe, saw what happens to it, and from that we come up with the conservation of mass equation. And the calculus behind that is on page 49 and following. What happens here is that we end up with that the change of the mass of the control volume with time is equal to m dot in minus m dot out. And you're going to say, thank you very much, I knew that to begin with, and for steady state, we're going to have m dot in equals m dot out. And so we have that, and that's our conservation of mass, but it's not in terms of measurable properties. So now what we do is we have the mass flow rate in terms of measurable properties. And so m dot is rho AV, density, kilograms per cubic meter, square meters, meters per second. And that's velocity. So this is your velocity. And so if I cancel this, we end up with kilograms per second. And so the mass flow rate can be written that way. We could also write it in terms of specific volume. M dot is equal to area times the velocity divided by the specific volume. And that's why I mentioned in the last chapter that we want to pay attention as to how you write this so that things don't get messed up. So this gives us that part. Now what we're going to do is transition to the first law of thermodynamics, which is conservation of energy, but first we have to define what the energy terms are, and we will start with work. So work, as you probably know, is force acting through a distance. And so we have del W is equal to F dx. And if I look at this, this is newtons and meters. So the units on this, a newton meter is a joule. And so the terms of energy are measured in joules, and I have a newton meter or joule, whatever. And work is not a property. Work is something a system does or receives. So if I were to take a chair and move it, so if I were to move a chair and I were to move it in a straight line, I have a force through a distance. If I did it like this, all over the place, the distance changes and the work changes. So I can't have, the work depends on how I get from 1 to 2, so it is not a property. Let's draw a piston cylinder. We're going to use piston cylinders a lot in this course, simply, and part of why we use them is it enables us to visualize things simply, and so, and that helps with what's going on. So I have a piston cylinder, I'm going to have my system, I'm going to have the surroundings, and what we have is, so if I have the system and it expands, so that let's say we have expansion. So the system does work on the surroundings. So we associate that with a positive sign, so we have the system do work for us, it's a positive sign. If we're compressing it and we have to put work into the system, we're going to have it be negative. So if I have compression, work into system, has a negative sign associated. And that way, just like up is positive, down is negative in terms of math, what we have here is the system doing work is positive or a good thing, the system receiving work is negative. And so let's look at how we can define this. So now let's take this piston cylinder. So we'll do this and we'll develop an expression for work in terms of properties. I have the piston cylinder, it has an area A, and here's the system. And let's have the system expand, so I'm going to have dx, and then eventually it'll be down here at state 2. So I'm at state 1, going to state 2, something like that. And the system's going to expand, so I could look at a PV diagram. And so I have a PV diagram, something like this. At state 1, we're here. And then at state 2, we're down here somewhere. And now what I want to look at is, let's have a system path that goes from 1 to 2. So I have our path, which we talked about in chapter 2, going from 1 to 2, and we want to find out what the work is. So let's look at what that will be. So we know that force, that del W is equal to F dx. F is equal to the pressure in the system times the area. So we have that del W is equal to PA dx. And A dx, so the area of the piston moving is a change of volume, so that's dV. So we have that del W is equal to PdV. And I could integrate this from 1 to 2, and I would have W12 is equal to the integral of PdV from 1 to 2. When we did this, notice I'm writing this, and I drew a continuous line, so this was a continuous function. So this is for equilibrium or reversible processes. And what happens in thermodynamics when you draw a straight line, since it's defined and I know how to go this way, 1 to 2, I know how to go back, and that means it can reverse itself. And that's why they're called equilibrium or reversible processes. Now, so now if I look at this, this area here is del W. And as you, so if I integrate this, you know from calculus that the line integral is the area under the curve, and so the area under the curve for this is your work from 1 to 2. So that gives us 4 equilibrium or reversible processes. And now let's do an example illustrating this. So we're going to have gas in a piston cylinder. Has an initial volume of 0.01 cubic meters and a final volume of 0.04 cubic meters. And an initial pressure of 400 kPa. And we want to find the work for this process for a couple of different paths. Work for A, P equals C, and B, PV equals C. So we have 2 different processes that we want to consider. One where the pressure is constant, one where the pressure is inversely related to the volume. And so what we did, and what I'm going to talk about in terms of thermodynamic problem solving, is that we drew a sketch. So the first thing in terms of problem solving is I want to translate the words into a sketch. So I have to do that. So now I'm going to have a sketch. And we'll translate it, so I have 400 kPa, 0.01 cubic meters, with state 1, and V2 is 0.04 cubic meters. And so the purpose of drawing a sketch is to take this information and transform it into visual information. Very often people say they're visual learners. You have to think of things visually. So one of the challenges in thermodynamics is reading words and try to find equations to stuff them in, rather than drawing a sketch and thinking about what's happening. And so I want you to think about what's happening. So we did a sketch. We talk about what is the system. Is it open or closed? In this case, it's closed. And is there a process involved? And right now, yes, there's P equals C process is the first one we'll look at. So now we're going to apply what we know about work for a constant pressure process. So if I do this, W is equal to the integral of P dV. P is equal to C. So W12 is equal to P times V2 minus V1. The P comes out from the integral sign. We have dV, and so then we have that the work from 1 to 2 is equal to 400 times 0.04 minus 0.01 is equal to 12 kilojoules. I have 12 kilojoules represents the work, and if I were to draw a PV diagram for this, we're going from 1 to 1, and so the area under the curve is 12 kilojoules, and we see what that is. Now, let's do a slightly more complicated function. So we have PB is equal to a constant, or P is equal to C over V. And C is equal to P1, V1 is equal to 400 times 0.01. So C is equal to 4. So now when I integrate this function, so I have that the work is equal to the integral of P dV. So the work is equal to the integral of C dV over V, or the work from 1 to 2 is equal to C times the log of V2 over V1. If I substitute in numbers, I have that the work from 1 to 2 is equal to 4 times the log of 0.04 over 0.01, which is 4. And in this case, we have that the work is equal to 5.5 kilojoules. And so here, so this was for P equals C. This was for PV equals C. And so I can see that the work for constant is 12, so it's a bigger area under the curve, a smaller area under the curve, hence the difference in the values. So for homework related to this topic, do 3.9, 318, ABC. And now what we want to do is to continue on with our discussion of work in reversible and irreversible processes and how we can use this in actual situations. So I want to discuss this, and so now let's see, we have this piston cylinder. And when I drew this line before, we talked about it from 1 to 2. So when I talked about this, I was looking at it, is like the pressure had to be defined all the way along. So that meant as this piston moved, the pressure had to be uniform throughout the system. So it has to move very, very slowly. If it's moving very, very slowly, how can I have this work? And so what happens is, so now I want, how can I use this? Why is it useful? And so the time to establish local equilibrium in this case uniform pressure is much faster than the macroscopic event the piston movement. So it's much faster than, so it appears that the pressure is uniform throughout the piston, even though it isn't, but from the macro perspective, it is.